So maybe we can get started here. It's 4 o'clock now here in Denmark. So we're very pleased to have Greg Moore from Rutgers, and so you can see the title right here. It's Summing Over Bordisms in TQFT. So Greg, please, the word is yours.
Well, thank you for the invitation to talk. I'm not quite sure who I'm thanking and where I'm giving the talk. I mean, let's see. Oh no, my thing is not advancing. Why is that? Uh-oh. Oh dear. Okay, just encountered a technical problem. Let me plug this in and out. My clicker is not advancing. Oh, good heavens. Okay. Let's try again.
But we all have your slides anyhow. You can,
yeah. Why are there two? Okay. Let me quit. Yeah, but I mean, if I can't advance the slides, that's not going to work. So let me try again. Okay. That is really bad. Let's see. I'm just going to... Now the clicker's not working.
Now the clicker's not.
Yeah.
Are you sure you put the thing in?
I am quite sure, and it's on. All right,
Where's
let's
the
try.
clicker?
It's all plugged in. So now let's see. All right, I'm bringing it up again. Okay. Now if I do a slideshow from here, I know I have to share it. Okay, so it works. Clicker works fine. Clicker works fine when I do it on my computer. Now I'm going to share the screen. And let's go from the beginning. Yes, all right. Okay. That's because Karen's here, yes. All right, so thank you for the invitation to give this talk. As I was saying, I'm not sure where I'm giving the talk. Maybe I'm giving it here, or maybe I'm giving it here, or maybe I'm giving it here, or maybe I'm giving it here. Well, wherever I'm giving it, the title of the talk is Summing Over Bordisms in TQFT. And this is work I did with my graduate student, Anindya Banerjee, who will be a postdoc at Queen Mary in September. So here's the outline for the talk. Let me begin with some quick motivation. And the motivation comes from quantum gravity. Now, I don't know what quantum gravity is exactly, but we don't really need to know. There's a long-standing problem in quantum gravity. So roughly speaking, quantum gravity is supposed to compute probability amplitudes by summing as in a path integral over metrics on some space-time. And maybe we'll weight it with something like this, like the Einstein action or some modification of the Einstein action. And the long-standing problem is, if we sum over metrics, should we also sum over topologies? Well, in one of the best controlled examples of quantum gravity, ADS-CFT, there are clear indications that we should sum over topologies. So for example, there's the Hawking-Page transition, which is beautifully interpreted as the confinement-deconfinement transition in Super-Yang-Mills theory. One of my favorites is that if you make a Poincare series or a Rademacher expansion of the elliptic genus of K3, you can interpret that as a sum over topologies in ADS3-CFT2. And there's been a lot of activity recently in understanding the Page curve that plots the growth of entropy versus time in a black hole. And in the context of the information loss problem, there's a funny curve called the Page curve, and people have discussed this and claim to derive it using dominance of different topologies related to black holes. But if you sum over topologies, there are also some, if you introduce non-trivial topologies, there are also some non-trivial puzzles in ADS-CFT. And one of the basic points is that you can have a hyperbolic manifold Y where the boundary has multiple components. And that's simple enough in mathematics, but that leads to some puzzling aspects of the ADS-CFT correspondence called the factorization problem. And a few years ago, Saad, Shenker, and Stanford wrote a very beautiful paper identifying the sum over topologies in a two-dimensional model of quantum gravity. They identified that with a matrix model. And then that raised some important conceptual problems about whether string theory should be dual to an ensemble of quantum field theories. So motivated by these issues and the recent vigorous discussion in the quantum gravity community, Don Maroff and Henry Maxfield considered a curious topological model of 2D gravity. And an essential part of their discussion involved summing over topologies with disconnected components. So my project with Anindya Banerjee was motivated by the desire to understand the Maroff-Maxfield model in terms of standard TQFT. And I'll comment on the Maroff-Maxfield paper towards the end of the talk if there's time. So it's almost certainly not necessary for this audience, but let's go quickly through some reminders on TQFT to set some notation. So first of all, what's a Bordism? So if X in and X out are smooth, compact manifolds of dimension d-1, a Bordism, Y, from X in to X out, is a D-manifold Y together with a disjoint decomposition of its boundary, and diffeomorphisms from those partitions of the boundary into in and out parts with X in and X out, and embeddings of little collars around X in and X out into Y. And those embeddings have to reduce to the specified diffeomorphisms on the boundary of Y. So that's the official definition of a Bordism. So for example, if we have X in is 3 unoriented points and X out is 5 unoriented points, then here's an example of a Bordism, one manifold whose boundary is as X in and as a decomposition into X in and X out, the red and the purple. And if I counted right, there are 105 such Bordisms. So there could be many different Bordisms between a given X in and X out. Now, Bordisms are morphisms in a category of d-1 dimensional manifolds as objects and d-dimensional Bordisms as morphisms. And for purposes of this talk, a topological quantum field theory is just a monoidal functor to the category of vector spaces over a field kappa.
Greg, can I ask an annoying question?
Sure.
I would have thought there were infinitely many such Bordisms because you could just put disjoint circles as much as you want.
Thank you. You're right. You're right. And that actually will be an important part of my computations later. So what am I trying to say here with the 105? Yeah, I guess there are 105 that don't have those extra disjoint circles. And I won't even swear to that. The main point I was trying to make is that there are many. But you're absolutely right. There are infinitely many Bordisms. So the main idea is to a d-1 manifold X, you associate a vector space of states for your spatial manifold Z of X. Whoops, going the wrong way. And then a Z of a disjoint union is the tensor product of the state spaces. And if I have a morphism Y from X in to X out, then Z of Y is going to be a linear transformation from Z of X in to Z of X out. So we'll look at d equals 1 unoriented Bordisms, and then topological field theory is just determined by a finite dimensional vector space, namely the value on a point, and a symmetric non-degenerate bilinear form, which is determined by this diagram. In the two-dimensional case, and I'll just consider the oriented two-dimensional case, there are several flavors that you can study. So we can talk about closed and semi-simple, and then we have complete results for that. Open, closed, and semi-simple, we have complete results for that. In the closed and non-semi-simple, well, we worked out some examples. And for the open, closed, non-semi-simple, we didn't really think about it. So a D equals 2 closed-oriented TQFT is determined by a commutative Frobenius algebra. So I'll denote that by C for closed. So that's the value on the circle. And then if I consider the disk as a Bordism from an ingoing circle to the empty set, that defines the trace function from C to the ground field kappa, so that if I consider the bilinear form where I multiply and take the trace, that's a symmetric non-degenerate bilinear form. And I'll talk about the open-closed case later on. Okay, so now I want to define the sum and total amplitudes and talk about the splitting property. So as I stressed, we can have different Bordisms between a fixed x in and x out. And so now, given a topological quantum field theory, Z, which I'll call the seed topological quantum field theory, we can define the summed amplitude where we sum over all the Bordisms. We take the linear transformation Z of y and we divide by the order of the automorphism group of the homeomorphism type, which restricts to the identity on the boundary. So here again is that definition. That's the main object of study in this talk. So what are some questions we want to ask about this? First of all, does it exist? If it exists, is it computable? And if it exists, then what properties might it have? And so far, I've only looked at the top 2 categorical levels. It's natural to ask if you can extend it to the fully local TQFT. So here's some answers. Yes, it exists for 1 and 2 dimensions and does not exist for 3 and higher dimensions, at least not in the most naive sense. So that seems to me a very important open problem. What to do about that? Now, in 1 and 2 dimensions, at least in all the cases that we've thought about, yes, you can compute it. And from the explicit computations, we observe something called the splitting property, which I'll explain in detail. And, well, the issue of extension to the fully extended case is only really there for 2 dimensions. And in this case, that's equivalent to the extension to the open-closed TQFTs. So I'll explain that later. So now, in studying these summed amplitudes, it's actually very useful to consider all of the summed amplitudes simultaneously as a single linear transformation from the tensor algebra of the direct sum over these state spaces, where I take the direct sum over all smooth connected d-1 manifolds. So that's what the complete amplitude is. So this takes into account all possible ingoing manifolds and all possible outgoing manifolds, and we just sum over all those possibilities.
Oh, maybe it's not tensor algebra, symmetric algebra.
Ah, thank you, Maxime. Yeah. So because I'm summing over Bordisms, this actually, a priori, it only lives on the tensor algebra. And if you look at particular amplitudes and don't sum them over Bordisms, then they will only live on the tensor algebra. But because I'm summing over Bordisms, it will descend to the symmetric algebra. So Maxime, you're completely right. So the object of real interest here is the endomorphisms of the symmetric algebra. And I'll call that the Fock space of the seed TQFT Z. So A bar is what we want to study. Okay, now what is the splitting property? So you could probably do it for other fields, but I only really thought about it most for the complex field. So for K equals C, we can put an inner product structure on the Fock space of Z. And then there exists another inner product space, not necessarily positive definite, but there exists another inner product space so that A bar factors as phi times phi star. I couldn't figure out how to get Microsoft to give me a dagger, so I prefer phi dagger, but I have to use phi star because that's all that Bill Gates will let me do. So it's phi star. Phi star is the adjoint with respect to the inner product structures. where phi is some map from the Fock space of Z to W. So I'm going to call that the splitting property. Now let's make some comments about it. Why is it interesting? Well, first of all, as I just said, the inner products need not be positive definite. So it's not just that I have a positive map, and I always know a positive map is expressed as phi star.
Sorry, Greg. Sorry to be pest. How you multiply phi was operator from Fock space to your auxiliary guy?
Yes.
And A bar is operator from Fock space to itself. So I think it's phi star.
Okay, Maxime. I'm composing from left to right.
Right. Okay. Yeah.
Okay. So okay. I'm thinking of phi as living in Fock dual tensor W, and then phi star as living in W dual tensor Fock, and then I'm contracting the inner guys. So that's why I wrote it in that order, and it was just useful for writing the formulas.
I know. I remember many years ago you also proposed to compose from left to right, not right. Yeah.
Yes, the hop spaces. That's right. The hop spaces instead of the hom spaces. Yes.
Yeah. Okay.
Yeah. It's it's the same thing.
Okay.
Yeah. So it doesn't just follow because A bar is positive and you can always write something that way. Still, I am a little concerned that I'm giving a seminar on something which is an utter triviality, and maybe the splitting property is just some trivial consequence of linear algebra. When you try and make a careful proof of that based on that idea, I haven't succeeded. I'll come back to that at the end of the talk. But even if the existence is trivial on some general grounds, explicitly finding W and phi in examples is slightly non-trivial and amusing. Now, I do want to stress that the W is not unique. I could replace W by a direct sum of W's. And then if I have a set of positive numbers P alpha, which sum to 1, then I could simply take this direct sum here. So you might ask if there's a minimal W. And again, I haven't thought that through carefully, but you might ask if there's some minimal W so that all splittings factor through the minimal splitting. I don't know. But from the physical point of view, in some sense, W is the Hilbert space of a dual quantum mechanical system to the quantum gravity theory. You see, A bar is my toy quantum gravity theory, my topological 2D quantum gravity theory, where I'm summing over all topologies. And yet I can express all the amplitudes in terms of inner products, ultimately, in another space, W. So I like to think of it as a kind of dual quantum mechanical system to the quantum gravity theory. Now, quantum gravity specialists I've talked to don't like that interpretation. So the number 5 is definitely a debatable point. Another thing, a remark, is that this formula is a little reminiscent of the Steinspring theorem about completely positive maps. And I find it interesting because it seems to suggest a role for Hilbert's C-star algebras. And the reason I find that interesting is that a few years ago, just for fun, I wrote a paper trying to generalize quantum mechanics. The paper was called Quantum Mechanics with Non-Commutative Amplitudes. And the basic idea of that paper was, well, let's see if we can generalize quantum mechanics by replacing Hilbert spaces by Hilbert C-star modules. And then the overlaps of two, quote, wave functions is not a complex number, as usual in quantum mechanics. The overlap is an element of a non-commutative algebra, C-star algebra. And the point of that paper was, well, if you take that kind of setup, how in the world do you write a Born rule? And I solved that problem. But this is reminiscent of that, where A bar is expressed in terms of is expressed in terms of an inner product valued in a non-commutative algebra.
So what does this theorem says?
Pardon? Question?
What this theorem says, Steinspring theorem,
what does the Steinspring theorem say? The Steinspring theorem is a beautiful theorem about the general form of a completely positive map from a C-star algebra A to a C-star algebra B. And what it says is that you can always, there's always an embedding into the C-star algebra of bounded operators on some auxiliary Hilbert space, so that roughly speaking, the positive map is of the form 5-5 star. I've stated it a little bit roughly, but it's schematically of the same form. And the Stein-Spring theorem is a really important theorem, for example, in quantum information theory, when you talk about quantum channels and stuff like that.
Greg, just a question about summability. I mean, so far we've just been talking about formal sums, as far as I can tell. I mean, where are the, if you talk C-star algebras, you really have norms and boundedness and so on. Where's that in this picture?
It's not in this picture. So yeah, it's reminiscent of C-star algebras. I'm not, and I'm going to be a little bit careless about the difference between a Fock space and its completion. So when I say Fock space, you should take me to mean just the symmetric algebra. And you're right that there are a whole set of issues about completion and convergence. And well, I will be worried about convergence of my formulas. But when I talk about things like the Hartle-Hawking vector and covector, those are going to be formal objects and some completion of the symmetric algebra. And I'm not going to be careful about that stuff. Okay, so let's look at the example of d equals 1, unoriented d equals 1. So as I said before, Z is determined by a finite dimensional vector space, which I associate with point, and a symmetric non-degenerate bilinear form. So now my Fock space, as I was just saying to Jürgen, is I'm thinking of it as just the symmetric algebra. And we surely have to talk, if I were going to be more careful, I would have to talk about various completions of this. So let's start with the simplest case of all in our summed Bordisms, with x in and x out is the empty set. And so what are the Bordisms from the empty set to the empty set? Well, they're disjoint unions of circles, as Vivek reminding me. What's the amplitude for a circle? Well, it's just the dimension of the vector space. So now if we sum over all disjoint unions of circles, remembering to divide by the automorphism group, then as usual in quantum field theory, the relationship between connected and disconnected diagrams becomes an exponentiation. And so the amplitude from the empty set to the empty set is just the exponential of the dimension of V. So that was easy. Okay, now when we add in ingoing and outgoing states, it's actually very useful.
Sorry, Greg, you should divide by order of automorphism of the circle, by the order of symmetry group.
That's right.
And order of symmetry group, it's something which kind of number of elements is S1 or whatever different. It's something which you can.
So I have
some constant, yeah, which you put into the game.
Oh, you mean you want me to put in a constant? I guess I could put in a coupling constant.
Yes, because order of automorphism group, what is it? I don't know.
Well, what I mean is if I have a disjoint union of n circles.
No. We have automorphism of a circle, yeah, because we consider Bordism, we should divide by automorphisms, trivial and on the boundary.
Yes.
So it will be diffeomorphism of the circles, not only symmetric group, but this group of diffeomorphism of the circles. And which
I don't think we should do that because we're in a topological field theory.
Are you sure?
I am not sure.
Yeah.
I am not sure. What is done in the literature, what effectively is done in the literature, you're not going to find this particular example. I did this
but to mention high dimension, you have topological field theory. Okay, you can say what is
but I don't.
Manifold, but number of automorphisms. It's for me it sounds fishy. That
okay.
Only to connect component. Yeah, it's.
Okay. I'm very sympathetic to that.
Yeah.
I'm very sympathetic to that. I certainly worried about that, but what I'm doing is just, that's why I said the automorphisms of the homeomorphism type. which are 1 on the boundary. That's the rule I'm going to take. Now, I'm very sympathetic to that. One can consider other ways of dividing by automorphisms, and I think that would be interesting.
Yeah.
So does it mean
yeah.
that you declare it to be trivial on closed?
Yeah, it declares trivial on its
On a connected surface. That's right. So to be very concrete, if I have a disjoint union of n circles, then the automorphism group in question is just the permutation group. And so I'm just dividing by n factorial. So it's just the dimension of v to the n over n factorial, which is the exponential. It sums up to the exponential. That's what I'm doing. Now, I certainly agree that one should consider other alternatives to that, especially when we get to 2 dimensions.
It sounds like you're talking about a parameterized or rigidified theory.
Yeah,
right?
And also it's kind of arithmetically it's kind of unhealthy to write exponent of natural number. You try to exponent 2 pi I times integer number. It's yeah. It should put some coupling constant here.
Yeah. And actually, in the very definition of the sum, it's better to include the parameter. Then
Okay,
it will be easier to think about the convergence property because it's a formal series.
Well, that could be a serious remark when we come to 3 dimensions. Well, I'll talk about that later. Yeah, that could be a serious remark when we come to 3 dimensions. Yeah, okay. I think I better move on, but I'm definitely sympathetic to what you're saying. Anyway, so now I want to. That was supposed to be the trivial case. So now let's have ingoing and outgoing manifolds, and here it's useful to recall that because we have a non-degenerate B, they're canonical isomorphisms between V and V dual determined by B. So if we have amplitudes with n ingoing points and n ingoing points and n outgoing points, then by applying B upper V and B lower V, I can get all the other amplitudes with the total number of points the same. So that shows you that it's actually useful to calculate instead, and technically it's easier, to calculate what I call the Hartle-Hawking vector. The Hartle-Hawking vector is the sum of nothing to something. So mathematically, I take kappa, the ground field, I put it into the Fock space, I act with the total amplitude, and so if I apply that composition of maps to 1, I get a vector in the Fock space. That's the Hartle-Hawking vector. And here it's not actually in the symmetric algebra, it's an infinite series. Dually, the Hartle-Hawking covector is the sum of anything going to nothing. So here you take the total amplitude from the Fock space of Z to itself, and then you project onto the ground field. And so I'll denote that by psi Hartle-Hawking upper dual, and that's just an element of the dual space of the Fock space. So let's look at the simplest example. Supposing the dimension of our vector space is 1, ground field is C, we choose a V with B is 1. So now it's not hard to calculate that this is the Hartle-Hawking covector. So what do we have to do? We have to look at Bordisms from the number of points to the empty set. So supposing we have 4 points here, then you see here are the 3 Bordisms we have to do. And now to answer Vivek's objection from before, then those Bordisms have to be including in those Bordisms, I have to take all possible disjoint unions of circles. That's why there's the exponential of 1. 1 is the dimension of V. So I'm sorry that's unhealthy because we all have to stay in good health. But that's what we get. If we put in a coupling constant like Jan and Maxime wanted to do, we'd have something else there. Anyway, there are you see there are 3 Bordisms that are connecting points and don't have disjoint unions with circles. And we recognize that 3 very well. That's the number of ways of pairing up 2 endpoints into pairs, which we're familiar with from Wick's theorem. And so if I had 2 endpoints, I get 2n factorial over n factorial to the n. So that's the Hartle-Hawking covector. And now it's trivial now to get the total amplitude in this very simple case with one dimension, and that's the total amplitude. And so that's an element of S star of V dual tensor S star V and the endomorphisms of the Fock space of V. Okay, now let's look at the splitting. So as I said, you recognize 2 to the n factorial over n factorial 2 to the n from Wick's theorem. So it's this integral. So let's introduce L2 of R, that's going to be our space W, and a wave function psi sub n, which is just h to the n e to the minus 1/4 h squared. And then you see the inner product of psi n with psi m, well, it's 0 if n plus m is odd, and it's the desired combinatorial vector if n plus m is even. And so phi is just given by this formula here. So, so that's the splitting. And this generalizes very nicely to dimensions b greater than 1. One way of saying what the general formula is just to write the Hartle-Hawking covector on what I call the exponentiated diagonal. So we take a vector v in our vector space, and then e to the v is some element of the Fock space. It's 1 plus v tensor v over 2 factorial and so on. And if I give you a formula for that, then because psi Hartle-Hawking covector is a multilinear functional, that determines the formula in principle completely, and then you can apply B dualization B to determine the full amplitude. Okay, so this is the formula that you get for Hartle-Hawking covector on the exponentiated diagonal. It's very simple, and I've written it in a way that generalizes for all bilinear forms and for all vector spaces. Various formulae that are presented in the literature of Maroff, Maxfield, and a follow-up paper by Gardner and Migas, I think should be understood this way. They certainly didn't say it this way in terms of Hartle-Hawking covectors and exponentiated diagonals. They just give you the right-hand side. What I'm telling you here is that I think that's what the left-hand side should be. Okay, let's talk about the two-dimensional closed case. So I'm going to assume that the two-dimensional TQFT is semi-simple. So then I have a direct sum of our one-dimensional Frobenius algebras, and so those are generated by idempotence epsilon sub x. So epsilon x, epsilon y is delta xy times epsilon x. And then the Frobenius structure is just the value of theta, the trace on the idempotence, and so that's an element in kappa star. And when I wrote my paper on TQFT with Graham Siegel, we interpreted this as the two-dimensional topological string theory with a zero-dimensional target space. So the target space of this topological string theory is just the spectrum of the Frobenius algebra, a finite set of points. And the theta sub x should be thought of as the dilaton. So each of these points is a component of the universe. So the universe is a disjoint union of points. And the only aspect of string theory that survives in this super simple model is the value of this dilaton, which is the string coupling, or to be precise, theta on the component x is the string coupling in the x component of the universe to the -2 power. Okay, so now we can go through the exercise we discussed before in one dimension. Now, if we look at the Bordisms from the empty set to the empty set, at least, all of Maxime and Jan's objections apply equally well here. We are taking...
I'm concerned that their objections are more serious here, because now automorphisms of a surface...
You're thinking about complex automorphisms of the Riemann surface? I mean, sure, the mapping class groups are much more interesting, and I guess we could try and divide out by some volumes of the regularized volumes of the mapping class group.
But you don't do this.
No. What I'm doing is very simple-minded. So your general Bordism is going to be n0 zero dimension genus 0 surfaces, and n1 genus 1 surfaces, and disjoint union n2 genus 2 surfaces, and so on. And then automorphism group of that thing is just the symmetric products of S sub n0 times S sub n1 and so on. And so this exponentiates to a sum over the connected Riemann surfaces. And then that is simple exercise in topological field theory. That's just the trace of 1 over 1 minus h, where h is the handle adding element inside the Frobenius algebra, which is defined by a one-hole torus with an outgoing circle.
No, but Greg, I really don't like this counting automorphisms of connected surfaces as one. It's because in 3-dimension get finite groups of automorphisms, and it should be really close to earlier characteristic of moduli space. That is Bernoulli numbers. It's
again, I'll just repeat what I said before. I'm actually quite sympathetic to this.
Yeah, and also you'll have the same problems with surfaces with boundaries, yeah, and different automorphisms identical on the boundary, which is again.
Oh, no. We have to. I mean, to get nice formulas, we have to restrict to the identity on the boundaries.
Yeah. So you have surfaces with boundaries.
Yeah, you still have some.
Order of automorphism group we should interpret in some way. Besides, it's just counting by zero.
I like what you're saying. I definitely like what you're saying, but I definitely cannot do it in real time.
Yeah. Okay.
We're just. This is what people were doing in the literature, and so the task I set myself in India was, okay, there's this paper from Merolf and Maxfield. Let's try and understand it in mathematical terms. So this is what they do, and in particular, I mean, I really struggled with the condition with the way they were counting when they had non-empty ingoing and outgoing manifolds, because what seemed natural to me was not what they did. But I'm going to be counting the way they did, and I quite like what you're saying actually, because as I'll stress later, this will only go up to 2 dimensions, and we would love to go beyond. So maybe this is a way to do it. Okay, so this is the general formula for any 2D TQFT, and if I have a semi-simple TQFT, then this can be simplified to an exponential of the sum over these space-time universes, the components of the universe, where lambda sub x is just the geometric sum. So that's just the value of the sum of the partition functions for the connected surfaces of genus G. So it's just a geometric sum in the string coupling, which is theta x over 1 minus theta x inverse. That's the geometric sum of the string couplings. All right, so now let's ask what happens when we have a non-empty boundary. So let's take the simplest case. Let's think about the Hartle-Hawking covector, where we have 2 ingoing circles and we're mapping to nothing. So for simplicity, I'm going to take the dimension of C equals 1. And so then phi1 and phi2 are just multiples of the idempotent epsilon. And so now let's talk about Bordisms with one connected component. So they're going to look like this, okay? And so what's the contribution of these Bordisms to the total sum? Well, I'm going to have the product of C1 and C2, and then the sum over the genera. And that generalizes. So if I have Bordisms with one connected component in n ingoing circles, and I sum over the genus, then I'll just get the product of the z's times this lambda. But now returning to the question about 2 circles at the top of the page here, if we have 2 ingoing circles, we can also have Bordisms with 2 connected components, like the ones I've shown here. And then we can add handles at will to the various components. And so then that maps Z1, Z2, phi1, phi2 to Z1, Z2 times lambda squared, because this sum here will factor as a product of the sum for the one ingoing circle with one connected component. So altogether, when I put back in the Riemann surfaces, which are just floating out there, which are Bordisms from 0 to 0, they give me a factor of e to the lambda, and then I sum over these other two guys, and I get lambda plus lambda squared. Okay, now lambda plus lambda squared is a polynomial I'll call B2 of lambda. And Maroff and Maxfield recognized that this B2 of lambda is a Bell polynomial. Okay, I had to look up what a Bell polynomial is, so let me tell you what it is. So the Bell polynomial Bn of x1 through xn is a polynomial that counts the ways a set of n elements can be partitioned. So the coefficient of x1 to the k1, x2 to the k2, and so on, counts the disjoint decompositions where we have k1 subsets of cardinality 1, k2 subsets of cardinality 2, and so on. And so I'm going to define Bn of lambda to be the Bell polynomial where all of x1 through xn are put equal to lambda. So the basic idea here is that if I have a Bordism from 1 to n, I have a Bordism of n circles to the empty set, and I divide that Bordism into connected components, and let's forget about the Riemann surfaces, which are just going from the empty set to the empty set, factor those out. If I divide that Bordism into connected components, we'll have kj connected components with j ingoing circles. And each of those components I showed you before, when summed over handles, gives a factor of lambda. So the upshot is that the Hartle-Hawking covector is given by this formula here. We're in the one-dimensional case here, one-dimensional Frobenius algebra. Okay, and now we can easily get the general amplitude. So here it is. So here's the general amplitude, the summed amplitude for this dimension 1 case. Now, these Bell polynomials have an interesting relation to coherent states. So consider the Heisenberg algebra, the bosonic Heisenberg algebra. And inside the Fock space, we can define what's called a coherent state, which is this, by definition, this thing here, the exponential of the square root of lambda times the creation operator, a dagger. And if n is the number operator, then e to the lambda Bn of lambda, it turns out to be the expectation value in a coherent state of the number operator to the little nth power. And from that formula, if you expand in the number basis, you get a very useful formula for e to the lambda times Bn of lambda, which is lambda to the d over d factorial weighted by d to the n. And this formula was used extensively in the Maroff-Maxfield paper. Now, it's also very useful to us for our splitting formula because here's a bar, here's the total amplitude, and now I remember that I can write e to the lambda Bn of lambda this way, and so I just substitute like that, and the basic idea is that, you see in that sum over d, you have d to the ni plus d to the ni times d to the n0, and that kind of factors between the in and outgoing states. So what I do is I use the Frobenius structure to give me a canonical real structure and a sesquilinear linear form, so I can take an adjoint. And if I take the adjoint, this is how it works on epsilon. So the splitting space will be again the Fock space of W. And if theta is real, but not necessarily positive, I can write phi as phi star this way, where phi is given by this explicit formula. So the idea is that this epsilon to the d, when I take phi star, it contracts with another epsilon to the d dagger. And when I do that, I have a square root of lambda to the d over d factorial squared. So that's the lambda d over d factorial. And then you see the d multiplying the epsilon check as the factor of d to the n in. And the other one from phi star is d to the n out. Okay, so let me make a few comments about this. The amplitudes here it's clear, can be invariant under the action of non-trivial global symmetry groups. So in the one-dimensional case, the orthogonal group of our bilinear form, or in the two-dimensional case, the automorphisms of the Frobenius structure. And that's a kind of interesting remark because there are many papers in the quantum gravity literature that argue that you cannot have global symmetries in quantum gravity. Now, there's no contradiction here because those papers use various physics of black holes. But I just want to point out that in this very, very baby simple model of quantum gravity, well, yes, you can have global symmetries. And similarly, there are also papers that say that quantum gravity can't depend on continuous parameters. But here we clearly have continuous parameters. We have the Frobenius structure and the orthogonal and the symmetric bilinear form. And if we start putting in these other kinds of automorphism groups that Maxime and Jan wanted to do, then we'll have more parameters. So yes, they're parameters. Now, another comment is that the Hartle-Hawking vector is the sum over all the amplitudes to go from nothing to something, and the Hartle-Hawking covector is the sum over all the amplitudes to go from something to nothing. So you would have thought, I would have thought, that if I contract the vector with the covector, I would get the vacuum to vacuum amplitude. That's completely false. In fact, that contraction of the Hartle-Hawking vector and covector is divergent. Maybe if we weight the automorphism groups in a different way, we can make it convergent. In fact, in the one-dimensional case, it's briefly mentioned in our paper that you could consider a different weighting of the different rule for the automorphism group, and then you could get a convergent inner product. But using the rule that people are using in the literature, this would be divergent. I found that surprising. Again, when I discussed it with a quantum gravity expert, he was not at all surprised, but I find it surprising. Okay, so now let me come to the open-closed two-dimensional case. Oh dear, I'm way behind. So again, I'm going to restrict to the oriented and semi-simple case. So the in and out manifolds are disjoint unions of circles and oriented intervals. The intervals are just one morphisms in a category of manifolds with corners. So here's an example of an interval. And then at the endpoints of the interval, you have to put boundary conditions. And those boundary conditions should be considered as objects in a category of boundary conditions. And then the topological field theory functor assigns to this interval, call this interval IAB, it assigns the Hom space from A to B, which I'll call O sub AB, because it's a bimodule for the algebra OAA and OBB. So now our surfaces are two morphisms in a two category, and the boundary of Y is now has a disjoint decomposition into three kinds of boundaries. There's the ingoing boundaries. In this case, we have two red intervals and a red circle, and an outgoing boundary, which is one purple interval. And then we have what are called the constrained boundaries, which are connecting the endpoints of the in or outgoing intervals to endpoints of in or outgoing intervals. So I'll call those constrained boundaries, and I'll denote them with dashed lines. And we can also have closed constrained boundaries if we change our Bordism category a little bit to allow such things. So there are really three conceptually different kinds of boundaries. There's the in and outgoing boundaries. There's the constrained boundaries connecting in and out to in and out endpoints of intervals, and the closed constrained boundaries. In the quantum gravity literature, this distinction between these three kinds of boundaries is not clearly made, and that's one of the reasons I'm making a big deal of it here. Okay, so let me show you the splitting formula in the simplest case. Now, for simplicity, and we can relax all these conditions, but just for simplicity, we'll take the closed string Frobenius algebra to be one-dimensional. All constrained boundaries are labeled with a single boundary condition A, and Hom AA is an algebra OAA. There will be no closed constrained boundaries, and all the in and out manifolds will be intervals IAA, so no in or outgoing circles. Okay, so now to express the sum, you have to introduce the open string coupling, so you have to take the square root of the Frobenius structure theta. So if mu squared is theta, mu inverse is the open string coupling, and then if mu is real and theta is 0, yes, we have a splitting formula, where now phi goes from S star of OAA to the L2 functions on a vector space well, it's L2, so it's isomorphic to its dual, but it's a little nicer if you put the dual there. So what's OAA? Well, the Carty condition implies that OAA is a full matrix algebra, not just a direct sum of matrix algebras. And so it's a matrix algebra of NA by NA matrices. And so E sub NA here is just the space of NA by NA Hermitian matrices. So now here's the splitting formula. So phi is a sum over little n. That's the number of ingoing intervals. And then we sum over pairs I1, J1 through IN, JN, and the product of EIA, JA dual, where EIJ is a basis of matrix units for OAA. EIJ dual is the dual basis. And then that multiplies something in the space W, which is a matrix model integral. So we have some matrix model potential, e to the minus a half u of h, times the product of matrix elements times the ket vector in L2 of the space of Hermitian matrices. And the matrix model potential is a Laplace transform of the exponential of lambda over the determinant of 1 minus s to the 1 over muth power. Kind of a funny formula. And of course, convergence issues here are rather delicate. And I've thought about them a little bit, but not too much. So this is really a formal expression. Now, there's a funny mathematical structure here, since we have some really great experts. I want to mention it. You know, you can use these amplitudes to define a set of multiplications from the nth symmetric algebra, nth symmetric product of O to O. And so that gives you a series of n linear multiplications, totally symmetric. And so M0 is this, and M1 is this, and M2 is that. So at first I thought, oh, maybe we have cyclic cohomology or maybe some L infinity type structure, and none of that works. So, so people who like L infinity and A infinity and such structures, here's a challenge. What in the world is this mathematical structure? I don't know. It might be some kind of infinity analog of a Jordan structure. I don't know.
But no relations between those MNs, yeah? Or what?
Pardon?
No
Can't hear you.
relations between those MN, since you are looking for L infinity or something.
Yeah. Well, there are no obvious relations. Yeah, there are no obvious relations. But there might be relations, Jan. I mean, these formulas are pretty complicated. Okay, let me make some quick final remarks. First of all, d greater than or equal to 3. So, as I've said several times in this talk, what to me is an important question here is whether we can extend these ideas to three-dimensional TQFT. Of course, the classification of manifolds is much more difficult, to put it mildly. But let's just consider, the simplest thing. What about the vacuum amplitude from the empty set to the empty set? So that would be, at least using the automorphism group the way I've been doing it, the exponential of the sum over closed connected three manifolds of the invariant for the three manifold Y. Now, among those three manifolds, we have included the circle times the Riemann surface. But then the partition function in that case is just the dimension of the space of states on the on a Riemann surface genus G. And in our standard fully local topological quantum field theories, these state spaces grow with the genus G. The dimension grows with topological complexity. And the sum is irretrievably divergent. So you might ask yourself, could you have the dimension of z of sigma g equals 0 for sufficiently large G? And I was talking to Sergei Gukov about that, and he pointed out the answer is no, because for any three manifold, you can cut along the boundary of a handle body for any genus. You just take a little 3-ball, you put in a handle body of genus G there, and you have a decomposition into the handle body and the rest. And if the surface, if the state space for sigma G is 0, then the amplitude is 0. So if the dimension of the state space is 0 for any G, then all the amplitudes vanish. Again, something that took me by surprise, although the argument is very easy. So that leaves ourselves with the question of, is there some way to modify the domain and or the codomain categories to produce interesting examples in higher dimensions. Well, one thought I had was that Anderson and Kashayev found the notion of categoids to be useful in their study of non-compact three-dimensional Chern-Simons theory. And so I wonder if they could be useful here. And now, listening to Maxime, it's clear that maybe another route would be to think harder about these, generalizing these automorphism groups. I quite like that remark. All right, I am out of time, so I'm not going to, I had a number of comments on what Maroff and Maxfield actually did in their paper, but I think I'm going to skip that because I'm out of time, unless people want to hear it. And so let's summarize. So for suitable parameters of our TQFT, the total amplitude has a splitting, where phi goes from the Fock space of Z to some inner product space W. And I stress the semi-simple case because that's the easiest to explain in slides. But we also worked out some examples of non-semi-simple D equals 2 TQFTs. And it can take a little bit of ingenuity in specific examples, but we found this splitting always exists. Now, so there are many possible extensions of the two-dimensional results. So the general non-semi-simple case, both open and closed, remains open. Certainly, we ought to have been more systematic about various tangential structures. So, what about the two-dimensional unorientable case, or pin or spin structures, and so on? So we didn't work through that. One could also consider G equivariant theories, where you consider the Bordism category to be principal G bundles. And closely related to that is coupling this to two-dimensional Yang-Mills theory and generalizing topological field theory just a little bit by including non-trivial area dependence. That's something we're thinking about right now. And I think one interesting question is, what do you do in topological string theory? Well, I mean, all these ideas, of course, in the topological string partition function that is very much studied by many people, including people on this in this call. That's the empty set to empty set amplitude. That's the so-called easy part of this story. So now, what if we take the quantum cohomology and look at the Fock space on that quantum cohomology? Do we get interesting amplitudes? Could we say anything about them? Does the splitting principle, does the splitting property continue to hold? And so, speaking of the splitting formula, I keep worrying that it's just a triviality. It's a trivial consequence of linear algebra. And so the rough idea for that is the following. So this total amplitude should in some sense be symmetric under exchanging all the ingoing boundaries for all the outgoing boundaries. Because after all, what is a Bordism? A Bordism is just a decomposition of the boundary into in and out. So I could exchange the two. But at least for a finite dimensional complex matrix, if it's symmetric, then it can be written as phi transpose. It's just a basic fact of linear algebra. So I haven't been able to take that intuition and give a real proof of the splitting formula in all these examples. And if it doesn't follow by a linear algebra, then what's the a priori reason why it should hold? And finally, again, to stress the really important thing to me is this is all very limited if we can't go beyond 3 dimensions. So thanks for your attention.
Okay, so thank you very much for your talk. And let's have some questions, please.
Yeah. Oh, Greg, actually, I have a suggestion about 3-dimensional story. There is a kind of, I have a conjecture for 25 years, which is not yet proven, but almost close with Poincare conjecture, things like this. If you take any 3-dimensional manifold with, let's say, with boundary connected manifold and consider diffeomorphisms which are identical in the neighborhood of some point to kill torsion, then the classifying space is a finite CW complex.
Classifying space
of diffeomorphism group, and you kill torsion, say diffeomorphism identical on neighborhood of some point.
Okay.
Yeah, the classifying space is a finite cell complex.
Okay.
This is almost proven now, but it's not yet. And this is in Kirby's book of problems, low dimension topology suggestions in late 90s. But yeah, so this is conjecture which I had actually in my childhood when I read Thurston notes.
Oh, wow.
Yeah,
Okay.
yeah, and this seems to be true. And you see that because it's finite cell complex, it has finite Euler characteristic, and this will be something like 1 over order of diffeomorphism group roughly. Yeah, so it seems that it's kind of there's a good chance to define some reasonable.
That sounds that sounds fascinating. That sounds really fascinating. I like that. So it would be fun just to take, you know, like the simplest case, like an invertible one-dimensional topological quantum field theory, and try and apply that and see if one could get something.
Yeah.
I mean, another problem, of course, is that it's hard to enumerate 3 manifolds, right? So
I mean,
we don't know. I mean, we don't know, you know, how to characterize the fundamental groups of possible fundamental groups of 3 manifolds.
No. By geometrization, we have complete picture. It's connected sums of 8 geometries, and
all of them according to volume, right? Because there's only finitely many volumes, so the same. I mean, finitely many manifolds, same volume. And so I think it comes back to that. It's really important to have these constants going in, and not just summing without any regulating constants, or of course automorphisms. Anyway.
Sorry. Oh well, the regulating constants for me were going to be the the parameters of the topological field theory. But as I just argued, in 3 dimensions, that's going to fall flat on its face, because
I think you mean this missing replacement for the automorphism groups, not. For
Yeah. No, I pretty interesting.
Maybe I can continue on this path a little bit then. So when you looked at lower dimensions, it somehow just struck me that, you know, everything with the automorphism has been trivialized. So you don't divide by the automorphisms, and you don't have any spaces that includes actions of the automorphisms either. And so if you, for example, were to say that you want to understand, say, isotopy classes of embeddings of manifolds with boundaries inside other manifolds.
Yes.
Then, and that you have spaces attached to the surfaces where the Markman class group acts non-trivially.
Yeah.
Then that's kind of our starting point for discovering this geometric recursion, that we really somehow involved all of the structure that you have there, and then we ended up with this thing of summing over extractions of pair pans of surfaces. And you have to deal with that there are infinitely many terms in the sums, so you need to regularize the sums in some way, and so that's sort of why we've come up with this machinery of geometric recursion. And I was just wondering what would happen if you fuse what you are doing with this sort of more equivariant approach, that you're much more careful with automorphisms.
Yeah, I don't know. It sounds really interesting, actually. So yeah. If what you and Maxime are saying could be actually implemented to do something with 3 dimensions, it would be really great. Then there would be a path forward.
Yeah, and also it looks at the space. It's when you have cobordisms, you can imagine you start to make things like distance from one end to another end, and then with things meet each other, there will be middle surface, or middle things which separate your objects. Yeah,
I'm not sure I understand what you mean.
No. You want to say that?
I mean, the Yang Mills sounds a little bit like that, right? Then you have the area dependence.
Yeah, of course you have area dependence, but kind of morally, if you have some metric, you can imagine there will be some kind of like middle part of your cobordism.
Yeah.
Equidistances from the left and to the right, in a sense.
Right.
It could be singular variety, and it's in a sense you go through something and adjoint operator, so that will be the expression of your ethical phi times phi.
Oh, I see. You're offering an argument for why.
An argument, yeah. You're saying take a middle.
That's interesting. Could you say again? What do you think?
Yeah. No, if suppose your manifolds has metrics, yeah.
Yeah.
then for each point on the cobordism, you can consider distance to the boundary, and the close points could be on the left or on the right, yeah. Or some points in the middle. It will be really middle. The distance to the left and to the right will be the same.
Okay.
Yeah, so you kind of canonically decompose your space by some middle, and then it looks like exactly you're right.
Well, yeah, that's very interesting, but that gets to a deep issue. I mean, well, you know, something I think that's wrong with that is that you have to integrate over metrics. This is quantum gravity.
Yes, no, yeah.
So,
sure.
I mean,
but still, if you integrate, you get to take square of integrals in a sense when you give an intermediate object.
Yeah, I mean, you know, Maroff in Maxfield's paper kind of struggled with something related to this. They kept wanting to slice the surfaces in the middle and produce some kind of intermediate space, but then they got confused because, you know, there are many different ways of slicing and getting different topology. You know, obviously, you could slice the Bordisms in many different ways and get many different circles in the middle. So there was a very unclear story.
No, but if you do really, it's imagine there is some kind of integral over metrics.
Yes.
Then you have canonical splitting by
for each metric.
Integrate over remaining metrics on cobordisms. Yeah. Then you get canonical middle, and then it automatically have the structure. Your operator S will
but then you might have expected that the splitting space would always be the same as the Fock space, right? Because what would be in the middle?
Not really, because it's not exactly the Fock space, because the middle could be kind of singular surfaces.
I see.
Yeah, so it's kind of really interpolates between all of them.
Because in my examples, you know, the W in the two-dimensional semi-simple closed case, the W was the same as the Fock space. Yeah. But in all the other examples, W is different.
It's much smaller, yeah?
Well, I don't know. I mean, all Hilbert spaces are isomorphic. It's like L2. It's like I got L2 of Hermitian matrices of rank n. Yeah, and then I have to take, you know, I didn't show this part of the story, but if I included all the boundary conditions, then I have to do something like take a direct limit as n goes to infinity or something like that.
With Hilbert space, of course, equivalent, but there are functions of different number of variables, so it's in real life. So one can say what's bigger than another.
But so somehow the whole story reminds me a bit about what I was saying before about geometric recursion. Because what Max is proposing is some kind of solution where we haven't integrated over metrics yet. And that's sort of what we see in geometric recursion is exactly we build something on Teichmuller spaces.
Yes.
And then upon integration over Teichmuller space, we get something that satisfies topological recursion. So one could sort of aim for something before you integrate and get this decomposition up there. And then after integration, you're getting the decomposition you want. And so many things seems to point to that these automorphisms really have to come in and play, you know, a fundamental role. And this sort of decategorification has happened many times in your discussion. And one will discover a much more beautiful picture if you don't decategorify so many times.
Okay.
You can really work with the metrics on their spaces.
You know, I will make one remark. I mean, I'm very sympathetic to this idea of rating the automorphisms differently, as I've said about 10 times. But you know, in topological string theory, people also seem to take this for granted, right? Marcos is still here. Marcos, right? I mean, in the topological string partition function, what do? We say that the total partition function is the exponential of the sum over connected surfaces. And what is that sum? It's a sum of G string to the appropriate power times some integral over the moduli space of, you know, embeddings. So that's the way it works. And so, you know, I mean, what I was doing here is also considered standard in topological string theory.
Yeah, no, but you see that it's kind of this geometric topological recursion. There is Max chain identity. You take sum of infinitely many like coprime numbers or geodesics, simple geodesics, and then Mirzakhani proof shows it's the same as topological gravity, this Witten model. Yes, so you see that's really something nice going with infinite sums. And, And then
Exactly, that's what I was kind of hinting at, because that's, the most fundamental first example of geometric recursion is exactly understanding that Mirzakhani's identity, the Mirzakhani-Maxian identity, gives you the volume of moduli spaces.
Right.
So yeah, I think that if one lifts everything one categorical level where you're kind of in some sense looking at partition functions that are kind of traces, where there's all of this structure acting on these spaces has been traced out already. And it would be very interesting to find these objects before that. And then
I'm not sure I completely agree. I mean, I'm actually talking about linear transformations from ingoing to outgoing spaces. I haven't. What have I traced out?
Well, the sort of a bigger space in which the mapping class group of that surface acts non-trivially, and you have operators there, and you're looking at a trace of that operator, and that's your linear map, because it's fixing boundary condition. 2 ends gives you a linear map, right? So that's the way I'm thinking. And so
okay.
Geometric recursion, exactly. That one has lifted topological recursion one level up and gets all this new structure and nice construction.
But I think you're thinking about the three-dimensional case.
Mm-hmm.
I think you're thinking about the three-dimensional case.
2 + 1 possibly, yeah.
Yeah, I don't really see. I mean, I'm not going to have a mapping class group action in the two-dimensional case, because my Hilbert space is that first circle.
Yeah, but maybe it came from there somehow, nevertheless.
Possibly.
Anyway,
yeah.
Any more questions?
I have perhaps a little bit naive question. So in 2D Yang-Mills theory, there is a coupling constant.
Yeah.
So once you integrate over topology and also metric, do you expect that to play similar role to the coupling constant that Maxime and Yen has suggested? They will appear in the exponential, and I assume that you also need to introduce some cutoff, so then it's a dimensionless coupling constant.
Yeah, I mean, in the 2D, I think that coupling will play a role. I mean, well, I'm actually confused about it. So you see, since it's gravity, you're going to have to do an integral of A over the area. So you're going to get something like this. For SU2, you're going to have something like the sum over n of n to the 2 minus 2g. You're going to have to sum over g, but you also have e to the minus area times n plus 2, the Casimir of the n-dimensional representation. Then I'm going to have to integrate over A. So, so your question is all about really about the measure of how I integrate over A, and so I think it's going to be dA times A to some power, and whatever that power is, well, that's a dimensionful. If it were dA over A, that would be dimensionless, and then the coupling would drop out. If it's dA over A to the 1 plus x, then it's dimensionful, and there has to be another dimensionful constant, and I'm going to get the coupling e squared times that dimensionful constant time to get a dimensionless result. So it's a good question. So it comes down to what is the appropriate measure to integrate over A, and I think that I guess that depends a little bit on exactly what theory of gravity you think you're coupling the Yang-Mills to. Yeah, I don't really know, but it's going to be something like that.
I see. But do you see this as a promising approach of solving the higher dimensional problem, coupling the theory to a theory that actually has area dependence?
Well, it was one of the reasons I think it was one of the reasons I think it's worth thinking through the 2D Yang-Mills, because I'm thinking of ways to suppress, you make sums convergent. I mean, the real problem in 3D is, we do have the geometrization, but still, is there really an effective way of writing the sum over connected surfaces and saying what the possible fundamental groups are? I mean, I love you guys because you're so positive. When I've talked to other mathematicians about this, You know, they get very downcast and they're pouring cold water all over me. You know, you can't possibly do this because because we can't possibly, you know, write down all the hyperbolic manifolds and so on. So, well, I don't know. But yeah, well, I mean, there are two questions here, actually. There are two questions which should be separated. One is, can you write down a sum that in 3 dimensions that exists? And then a separate question is, can you actually compute it? So, you know, maybe it exists, but we can't compute it with 21st century mathematics. But, you know, that's a possibility.
I think one shouldn't worry so much about whether it's divergent or not, right? I mean, we love divergent series here in this forum. so I mean, you know, if you can then subsequently prove that, you know, it's a Surrey class of some type, then we all happy, and it has all these beautiful resurgence phenomena.
Well, I mean, oh, okay. You mean you're using resurgence, but yeah, but I mean, in the example I gave in about the problem with 3 dimensions, it's worse than that. I'd have to put in some coupling to get an asymptotic series.
Right.
Right. I mean, I just had this, you know, growing sum of dimensions.
Yes.
How do I make sense of that? Your first instinct is, oh, well, just use zeta function. But wait a second. What if you have an invertible topological quantum field theory? Then the dimension is 1 for every Riemann surface. So then you have the sum of 1. So you have zeta of 1. So you're on a pole of zeta. So that's exactly what I meant when I said it's irretrievably divergent. You know, you could, you know, even zeta function regularization won't get you out of that. If there's a way of putting in a parameter like we've been discussing in this talk, if there's a way of putting in a parameter, then yeah, sure, then we could start to hope that there's a trans series or
just one comment, Greg. I mean, you were mentioning topological string theory, and there the sum actually diverges like 2g factorial. Each genus grows like 2g factorial. Right. And still, you know, one can make sense of that series in many ways.
That's right. And that would be essential. Yes, that's right. So that would be essential. Okay. So yeah, thank you, Marcus. So the analogous step in this talk was the total triviality that if I sum the geometric series, you know, that lambda, we get the sum of g to the -2 plus 1 plus g squares. So then we can all do that. And, you know, well, that's not a problem. But dealing with this in topological string theory, what you just said is what is going to be necessary. So what would need to do, Marcos, is do something similar. So you've thought about that a lot and given ways to define non-perturbative topological string amplitudes, Fredholm determinants and so on, for the vacuum to vacuum. Now I'm saying, look, let's consider the map from the Fock space of the quantum cohomology to the Fock space of the quantum cohomology. And I don't know what those amplitudes are. Maybe it might not be a big deal given the vacuum to vacuum amplitude, but certainly something more has to be done.
Yeah, definitely. Yeah. So is there any interpretation of the factorization in the topological string case? I mean, do you have any kind of hint of what this could be? I mean, you know.
Well, first of all, I don't know if it's true because I wasn't able to make my linear algebra triviality, make it a triviality of linear algebra. Maybe one of you can, but so I don't know if it's true, strictly speaking. But if it is true, yeah, what is the interpretation? I really don't know. As I said, I saw similar things in this quantum mechanics with non-commutative amplitudes. And so the interpretation I gave to those was that, I have a family of quantum mechanical systems over a non-commutative manifold. I mean, I could go into detail on that, but there was sort of a geometrical picture for what such a generalized picture of quantum mechanics would give you. I really don't know if that's useful.
But you see, I mean, but you really have to go into this in the generalization of quantum mechanics. I mean, you cannot interpret this in conventional quantum mechanics.
No, I mean, well, I mean, yeah, I don't have much to offer you beyond what I said. So I did point out that if you have the total amplitude, A bar is phi star, then then there's a procedure described in my paper within India where you can view gravitational amplitudes, the mapping from in and out in spaces to out spaces. You can view that as an inner product in a quantum mechanical system whose Hilbert space is W. So my take on that is, oh, this is a dual version of the same theory. I've got this quantum mechanics on the space W. In particular, I mean, you could say that the gravitational amplitudes are certain expectation values in a coherent state in the space W of some operators which you can interpret as universe creation and annihilation operators. That's explained in my paper within India.
Okay.
And so that is an interpretation of W as a kind of dual formulation of the same theory. Now, what that would mean in terms of topological string theory, I do not know.
I mean, in terms of hyperbolic geometry, I mean, it's really a well-known phenomenon that there is this spine that the surface deformation retracts onto, simply by looking at things that autogeodesics from the boundary and then looking at where they hit each other. So just measuring distance in, as Max was saying. And then there really is a graph in the middle that the whole thing splits into, and you can think of this hyperbolic surface as half of it going from some regular ins as U1 to this graph in the middle. And then there is the dual part of it from the outs to this graph in the middle. And so this spatially gives this space a factorization just like that.
Oh, that's really cool. Okay.
And so
again, you're ahead of you're several steps ahead of me because you're in 3 dimensions.
No, here I was actually
where I don't even know it exists, but I mean, but I like it. I mean, you're saying if it existed, this would be a way to explain the splitting.
Yeah, there. I mean, in 3
Well,
dimensions.
actually, let me ask this: is there an analogous statement in 2 dimensions?
Yes, I mean, I was actually telling you the statement in 2 dimensions.
Oh,
it's
okay.
a hyperbolic surface with geodesic boundaries.
Oh, okay.
But there is an analog of this in 3 dimensions, which is sort of a convex core of the hyperbolic manifold in the middle. But in this case here, it's very simple. It's just the graph that deformation retracts onto.
Okay.
And it's equidistant points. So it's points that have the property that there are 2 points in the boundary that are different, that have the same distance to the point. And that's just draws a graph where the trivalent vertices are the things that have 3 points on the boundary with equally distance to it.
Yeah, that's really interesting. So it's
a global construction all over the space, and it's a well-known construction that constructs equivalence between tight-middle space and then the combinatorial tight-middle space. Actually, so it's a well-known construction somehow.
Okay.
In hyperbolic geometry.
Okay, I didn't know. So that's interesting. If that would give a nice explanation of the splitting, that would be great.
And it's something we used in connection with this geometric recursion, actually, with Gaetong and more people to do something about correspondence between combinatorial tight-middle space and then actual tight-middle spaces.
Okay.
There's sort of a scaling you can do, and in one limit, the usual continuous theory scales to the combinatorial theory. Yeah, so it could be fun to see if one can prove your factorization by first lifting it to one categorical level and then actually doing it geometrically using Maxim's idea there.
That would be cool. That would be really cool.
So, more questions, anybody? Comments? Thoughts? No? Well, maybe we should we've been at it for an hour and a half now, Greg, so it's great.
Okay. Well, thank you. This has been very, very stimulating. Very, very interesting indeed.
Thank you.
Well, it was a very nice talk.
Yes, thank you very much.
Yeah.
Thanks, Greg.
Okay,
Hope to see you
Bye.
soon. Yeah.
See you soon, man.
okay.
Okay, thank you. Bye-bye.
Bye.
Right, bye-bye.